Oh, take a
So-
lab
What
in school.
function?
N factorial is n times, so just a quick review, right? Times ... down to 3 times 2 times 1. Yeah?
What?
It's an awesome definition.
Okay. So if I have 5 factorial, this will be 5 times 4 times 3 times 2 times 1, which is
120.
Close.
No, wait, that's 6.
It is.
No, wait, yeah.
It is.
okay. So one of the things we have to be able to do, nice 3 phones, is simplifying factorials. So for example, like if I have something like this, n factorial over n minus 2 factorial, we just need to be able to simplify this. So I would simplify n factorial into n times n minus 1 times n minus 2 factorial, right? And I'll stop there. I could keep going, but of course, these are going to end up canceling. So I'll just have n times n minus 1. Okay?
Makes sense.
And yes, factorials grow faster than all the other functions.
But why?
How do you prove that, Ms. Casey?
I don't understand why. Isn't like 5 times 5 times 5 times 5 times 5 bigger than 5 times 4 times 3 times 2 times 1?
That's like tetration.
I love titration, man.
Do you get what I mean? Like,
Smart ass, bro.
That's like titration.
Okay, so you're talking about like x to the nth power?
Talking about n to the x power.
Yeah, but n is going to be a finite number, right? What are you even doing?
What about x to the x? Is x to the x grow faster?
No.
do you get what I'm saying? You know, like that 5 times 5 is bigger. 5 times 5 times 5 times 5 times 5 is bigger than 5 times 4 times 3 times 2 times 2.
No, I think like like this. If you have like 5 to the x and x
Can we just
factorial,
move on?
x factorial is going to be
Guys, no.
Why?
Guys, you're
Why?
wasting time. Tyler
Because it
doesn't
builds
wanna
upon
watch
itself.
this.
Not actually comparing the right thing.
Guys, I'm telling you, Tyler doesn't want to watch this.
Right, because again, it's not, we're looking at it as it approaches infinity.
Can I sit on a calculator?
Okay, can we just do Taylor series?
Please, yeah.
Thank you.
Please do that.
Okay. So we're going to start off with Taylor series starting at x equals 0. Anything where the center is at x equals 0, we call that a Maclaurin series. Okay? Maclaurin series.
Is that like a type of Taylor series?
Yeah, it's like a subcategory. So a Taylor series is anything that is centered at x equals a, whereas the Maclaurin is specifically a would be equal to 0. Okay? So this is how we generate a Taylor series. We take f of 0 plus f prime of 0 times x plus f prime of 0 over 2 factorial times x squared.
No.
What's that?
Is it not F double prime?
Sorry, f double prime, f triple prime, and so on.
Oh, wow.
Okay?
This is one big definition.
Okay.
Isn't that if you have 0 there, isn't it just 0?
Well, it depends what the
Survey
function.
said.
It's so it depends what the function is.
Well, you're multiplying it by 0.
Survey says.
No. X is a variable.
I understand it. I understand
We make it
it.
20.
Okay.
It's just a ridiculous
X is
definition.
gonna stay there. Okay, X is going to be the polynomial or the series that we're like what we have left with.
What does the 0 do? I'm not really understanding.
Okay. So if you remember what we did so we did like an example of a geometric, and we said, okay, we want to look at it for values that are close to, well, we did specifically between 0 and 1, but the closer to, you can move your center wherever you want, okay? But you're not going to be able to use all series or Taylor polynomials to approximate a value unless it's centered close to that value. Okay, so we do Maclaurin series to approximate values that are close to 0.
I think it's between 0 and 1, right?
And then we'll look at what happens if we center it around other values. Okay, just let's take a look. Okay, so we want to construct a fourth order Taylor polynomial. So a Taylor polynomial will just be the series, but stopping after the fourth derivative at x equals 0 for this function, natural log of 1 plus x. Okay, so let's start. Let's just figure out f of 0. So that's just going to be 0. Now, f prime of x is going to be 1 over 1 plus x, which implies, good, right? Okay, so again, what we want to do is we want to go to the fourth derivative. Okay, so the second derivative is going to be negative 1 over 1 plus x squared. Yeah? So f prime of 0 is going to be, thank you, that's what I meant, negative 1. Yeah. What about the third derivative? That's going to be 2 over 1 plus x to the third power, which means the third derivative at 0 is going to be 2. We'll go one more. Remember, anything after the fourth derivative, or for and after, we can put in parentheses. So it's going to be what? Negative 6 over 1 plus x to the fourth, which means our fourth derivative at 0 is going to be negative 6. Okay, so the way we write out a polynomial, Taylor polynomial, it'll be p sub 4 of x. So the 4 represents the fourth order or fourth derivative that we go to. Okay, so if we go back to our formula, the first one is going to be f of 0, so that's just going to be 0, plus, now it's going to be f prime of 0 times x, so that's just going to be 1x.
Over 2 factorial.
The first one's going to be over, technically 1. Okay, so technically this would be over 0 factorial, and this would be over 1 factorial.
0 factorial is 1?
0 factorial is 1.
Is there a definition? Is there a reason why 0 factorial?
Well, if you think back to where do factorials come from, you said permutation. So how many ways can you organize 0 things? One way. Okay.
Negative 1 over 2 factorial.
So minus 1 over 2 factorial times x squared plus 2x cubed over 3 factorial minus 6x to the fourth over 4 factorial. Okay.
We have to do the plus dot 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 or not?
No, so because I specifically asked for a fourth order Taylor polynomial, which we use by taking just those 4 terms of the series. If I ask you for the series, then yeah, we would put dot dot dot. And then we would look for a general term, which we will also have eventually. Okay, so what does this look like in simplified form?
This
X.
minus 1/2 x squared.
So x squared over 2 plus,
1 x cubed over
2x.
yeah, and just think here,
Oh,
because 3 times 2 times 1 would be 3 factorial, so the 2's would cancel. You should hopefully see a pattern now. Minus, what's going to happen with the next one?
6 times 5.
6.
Yeah, because, so what happens with the 4 factorial? That's going to be,
It's going to still be.
so the 3 times 2 is going to cancel, so I'm just left with,
That's crazy.
So now that we come up with at least that pattern, you should already know or guess what's going to be the next one. Plus x to the 5th over 5 minus x to the 6th over 6.
How did they figure this out?
They had too much time.
How do they do this?
Okay.
Would never in a million years
Yeah,
thought
because
of
you're
it.
Adam. So.
You think to put the factorial of a number
I
or
would.
a
Okay.
function at 0?
I did not come up with it. Okay.
This case is meant to-
Clearly somebody came up with it. It wasn't Taylor. It was just named after Taylor. So
Was it Owen Casey?
What, is it-
I
is
don't
it
remember.
called
We looked
Casey
it up
series?
one time.
Casey series?
No one wants.
Okay. No, but it's okay. Let's look at another one. E to the 2x.
You got made fun of for.
So same thing I want you to do to the 4th order. So f of 0 is 1. Okay, f prime of x is going to be 2e to the 2x. So that means f prime of 0 is 2. The second derivative, you probably don't even need to do what's going to happen each time.
Or
Yeah, so the second derivative at 0 is going to be 4. Third derivative is 8. And the fourth derivative, 16. So we're doing the same thing. So this one's going to be a Taylor polynomial of order 4. So first one is going to be just 1 plus 2x plus 4x squared over 2 factorial plus 8x cubed over 3 factorial plus 16x to the 4th over 4 factorial. Yeah, now we can try to simplify it. Sometimes it doesn't simplify nicely. Sometimes leaving it in this form makes it easier, especially if we have to come up with a general term down the road. Because what happens if we try to simplify it here? Well, the 1 plus 2x I can't do anything with.
Just do 2x
2x squared.
squared. Kind of annoying.
Yeah, now it's kind of annoying. It's 4x cubed over, oops, that's supposed to be a 3. All right, and the last one turns into,
2 over 2.
yeah.
Why do they do that?
So in this case, I actually would prefer that one, but I'll accept either one. Okay, so there's sometimes in the previous one, it worked out really nicely when we simplified it to see that pattern. And other times it looks like there's going to be a pattern and then all of a sudden it doesn't work out nicely. So sometimes it's easier just to keep it in factorial.
Keep it in the first form.
It depends. You can leave it in factorial. If for like quizzes and tests, if you want to leave it in factorial form, sometimes it might be a multiple. This would typically be like a multiple choice type question.
So they would probably put in one or the other.
They'd have it one or the other. You just have to be able to do both. Okay.
And you never need to prove it.
Okay. 7th order Taylor polynomial.
In the exam, what do you need to order? Just like right now?
7.
Well, yeah, we're going to do the
7? 6.
we're going to do the shortcuts with the McLaurin series and yeah.
Just write a proof.
Wait, like the
There's a
column?
shortcut. Sometimes you have to prove it. Yeah. Sometimes you have to use sometimes we have to use the way you generate a Taylor polynomial. Yeah, because especially if it's not centered at 0, you have to sometimes generate it by hand. If it's centered at 0, there's usually a shortcut to find. Like this previous one, there's an easy way to do this without this work. Just sometimes you can't, so that's why it's good practice to do that.
On the test, are they gonna just ask us straight up, like, construct it like this type of question? They're just gonna ask us to. Okay.
There's almost every year there's a Taylor series or polynomial on the free response questions. It's a big one. So, yeah, you can't.
Oh, I have to keep going. Can't just go full. It just goes 0, 1.
So this one's 7th order, but don't worry. Every other one is going to end up giving us a 0. because if I do f of 0, that's going to be 0. So we're doing sine x. So f prime of x will be cosine of x. So the first derivative will be 1. The second derivative is going to be, yeah, because that's negative sine x. So I don't really have to worry about that one.
And then 1 or negative 1.
Yeah, so then the third derivative, hopefully now you can see the pattern. It's just going to go, yeah, so the third derivative is going to be negative 1, good. And then the fourth derivative is going to be 0. And then the fifth derivative is going to be 1. And then it's going to be 0. And then it's going to be negative 1. This will be one that you will use so often that you're not going to have to generate this stuff by hand. Sine and cosine are going to be also two of the Maclaurin series that are on page 11. Okay, so we want Taylor polynomial of order 7. Okay, so what's that going to be?
X minus x cubed over.
Okay, 0 plus 1x plus 0x squared over 2. I'll just write it out. And then minus x cubed over 3 factorial. And then plus 0x to the 4th over 4. You get the idea. X to the 4th.
Plus x to the 5th.
Oh, x to the 5th. Yeah, that helps. 5th minus 0.
Minus x to the 7th over 7.
Okay. This is an example where I would not do anything with the factorials, especially once you start getting to like 7 factorial. So we have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial.
Cosine was the same, but just the evens.
It's just the evens. Okay, now, what's the significance of this?
Like skip every other.
Because
Well-
we can deconstruct the graph of sine of x and turn it into a polynomial.
Yes. Okay, sine of x can be approximated by this polynomial. Now, if I took infinitely many of those terms, it would be equal to the sine function.
Wow.
For values close to 0.
Zilch.
So between like negative 1 and 1.
Yes.
What does that mean for value?
Okay, so let's say somebody have a calculator?
Yeah.
Okay, so give me sine of something that's really small, like sine of
0.000.
well, you can even do like sine of 0.1, let's say.
You want me to type it in?
What they plugged in.
Oh.
Yeah.
Okay, that's fine.
That's fine.
I get it. I understand now. I
You know
understand
the
now. I understand now.
Oops, that's supposed to be in my
We have a
notes.
way of approximating the.
2 weeks ago.
We have a way of approximating the function of sine of x for all values
saw that.
with a polynomial.
I saw how you solved it. I couldn't have found that.
So what we're basically saying, and this is the whole goal of this, is we're taking any function, we could take any function and turn it into a polynomial. And
But
we
only
will
for
be
certain
able
values.
to use that polynomial to approximate it with such accuracy.
So like, I
What
could
did
do,
you
like,
get?
Sine of 5.
Well, don't do sine of,
Could I
Again.
take sine of x sort of like centered at
listen,
5?
this only works for values close to 0. If I want to do sine of something else, I'll move the center point, but then I also have to adjust my entire polynomial.
What do you consider
What is considered close to 0? Like,
So when does it start to fall apart?
Well,
Oh, they're
That
literally
depends.
The same exact.
okay, what did we get for sine of 0.1?
0.099833342.
0.
But it's sine of
Okay,
close
they're
to
like-
0.
Well, it's going to
always
be 0, but
close
if you
to
actually look at the decimal approximation,
0.099833342.
so how many decimal places is it precise? The 5th decimal place.
My
That's
bad.
pretty accurate.
I bet I could do better.
Now, imagine if you just went one more place over. You'll have even more accuracy. If you went to the 9th or to the 11th.
If I put in 0.01, would be more accurate?
Yeah, of course, the closer we are to 0, the closer the accuracy.
So
As well.
There's no way to create a Taylor series for a function that works for all values of psi.
Yes.
That's unfortunate.
So I changed what
Taylor should have blocked in a little harder to just get this.
You will be able to. So if we're going to get to the next page where these are the ones that we need to know. So sine can be used so this should look familiar. This is what we just kind of proved, right? This is going to be true for all values of x. Okay? All right. So what about if it is now centered at x equals a? Well, it's the same thing, just instead of just x, it's x minus a, right? That's the Taylor polynomial, is the partial sum. Okay, so we want to find the Taylor series generated. So this time I'm looking for a series, so we're going to include the general term if we can. Okay? And we want it at x equals 2. Don't do it. I see you. So f of 2 is e squared.
It's gonna be the same every time.
Oh,
It's
and
a really good meme about.
Wait, f prime of 2 is.
don't do it. Don't be weird.
I'm gonna
Okay.
block it.
All right. So we want a Taylor series. So what's our first?
First term is
E squared. Plus. Now it's e squared times x minus 2.
Why does it go to 0 if we're taking the derivative of e squared?
No. You're doing the derivative of e to the x and then plugging in 2.
Oh, okay.
Sorry, I didn't show it that time, but f prime of x would be e to the x.
You never told us to what degree what
Oh, this one's a series, so we want to express it for infinitely many terms. We're going to use our sum. Okay? E squared what?
Times
X minus 2 squared over 2 factorial. Plus e squared x minus 2 to the third over 3 factorial.
I don't like this one as much.
Okay. We need a general term. No. A general term. General term means, can you express each one of these terms, but with n?
E squared.
So e squared
X minus 2 to the n.
x minus 2 to the n
Factorial.
over n factorial plus ... It's going to keep going. So that whole thing is equal to the sum n equals 0 to infinity of e squared x minus 2 to the n over n factorial. Because when we write it with our summation, that is our general term. And then just make sure, sometimes we start with n equals 0, sometimes we start with n equals 1. But this one we want to start at 0.
How are we?
Well, it has to match what our series is. So if I started with n equals 1, then it wouldn't include that first term. Usually it's going to start from 0, but there are exceptions to that. Good.
Well, but then doesn't it equal 0?
What?
If you plug in x equal 2, doesn't it give you?
If you plug in x equals 2, why would we? What? Or?
If you plug in x equal 2, so you just get like. No, you're plugging it in for n, not for n. You're plugging n and not.
The counter? The index?
No, I get that. But like, if you want to see now, that's equal to the e to the power of 2. No, that's equal e to the power of. What is it equal to?
What do you mean?
This Taylor series. What is it equal to? E to the power of 2. No, e to the power of x, not
E to the power of x?
around 2.
Is this just a way of approximating the function of e to the x at x?
Well, we don't know what x is.
Is it 2?
It depends what our value of x would be.
No, but then like if you plug in 2, if you want to check the e to the power of 2, you get 0, which is like not true. So, because that's equal to e to the power of x, right? And if you plug in,
If I plug in 2,
yeah, because I
it
want
should
to
be
know-
e squared.
But then you plug in x equals 1, it's zeroing it out.
Well,
Yeah, but this
That's
is
just a
just the
function.
general term.
Yeah. But
But
if
you don't
plug
want
in-
to put. But we're not just plugging 2 in.
It's gonna be e squared plus 0 plus 0 plus 0 plus 0 plus 0.
Yeah,
the first
yeah,
term.
yeah. That's what you get. The first term's always going to be e squared, no matter what. So you're always going to have that e squared, regardless of what x is. I mean, if x is 2,
But then you get a 0 to the power of 0. That's what I mean.
That's why.
Because that e to the power of 2, it generates from 0 to the power of 0.
anything to the power of 0 is 1.
But 0 to the power of 0.
So wait, is this function confirming that 0 to the power of 0 is 1?
But
So we
you're
should
not
write that.
you're not evaluating it for. You're evaluating a series centered at x equals 2. So, like, for example, you could approximate e to the 1.9 or 1.99, but you're not going to, there's no reason to do e to the second power using,
Yeah, 'cause you just got used to the second power.
yeah.
But we can't plug in 2 without the function breaking.
No, it confused me because when you plug into no,
But,
it's fine.
but yeah, but you're not plugging in x here.
Okay. I guess 2.
I mean, there will be a time where we want to evaluate it for values that are close to 2. But there's never a place where we would plug that. You're right. It doesn't make any sense.
Like, that seems kind of like
Okay. Let's
they kind of-
let's try one where we don't know what the function is. We just have these values with the derivatives.
It is.
Okay, we want to write a third order polynomial for f at x equals 1, and then we want to use it to approximate f of 1.2, right? Again, we wouldn't use it to do f of 1. We would use it to approximate something close to 1. So let's start off with the third order polynomial. Okay, so f of 1, 3, minus 2 times x minus 1. Don't forget, our center is now at 1. Then plus 6 times x minus 1 squared over 2 factorial. Right? Plus 2 times x minus 1 cubed over 3 factorial. Yeah. And now I want to use this.
So this is basically all just for like approximation.
This is all for approximations. So I don't know what my original function is. Okay? I just know that these are all my derivatives centered at 1. So I can come up with a polynomial, right, that will approximate those values. So I can find a very, very close approximation for f of 1.2. We'll do how close the approximation is. I mean, I know you guys plugged it into your calculator, but we'll be able to see how close this is. So it's going to be what?
3
Minus 2 times plus 6 times 0.2 squared over 2. You do not have to do this on your calculator.
By the way,
Just do it on your
is
calculator.
there should be over 6.
3 factorial.
Oh.
Is there a way to put factorial in your calculator?
Yeah.
Or you could do 1 over 3.
There, I meant to do that. It doesn't matter. Okay. 2.7.
2,
2.
6, 6, 6.
Perfect. 3 decimals is
Yeah,
good.
that kind of. I thought it was E.
So was it e to the x or the approximating e to the x?
No, I think when I made this example, I just gave random numbers. I mean, it looks like it's approximately E. I think that's just a coincidence.
I plugged it in and E to the 1.2 is like a little over 3.
Okay. These we want to put a big star next to.
Oh, these are, we need to learn these.
Okay, so one of these you should already know.
Yeah, the first one.
The very first one. What is the 1 over 1 minus x?
X plus X plus.
I know, but what is this? This is a geometric series with a common ratio of x. In fact, both of these are geometric series.
Nice.
The
Right.
functions don't really seem related.
This one, what's the difference between this one and this one?
And then it was
The negative. It's this one's an alternating series. This one here. Okay, so that should be no surprise. Here's our e to the x. 1 plus x squared over 2 factorial plus x cubed over 3 factorial, so on. Sine we just did, where we did a polynomial. And then I think, Adam, you asked, wouldn't cosine just be the evens?
Yeah.
And then natural log of 1 plus x. We also did that one.
Oh wait, and these work for all real X?
Yes.
Oh, that's the same thing. Okay, I'm cool with that.
Okay. So these work for common ratio less than 1, or the absolute value of it. These 3 are for all real x, and this one works between negative 1 and
But
1.
it also includes 1.
It includes 1, but not negative 1.
Yeah.
Yes.
Why?
Because negative one is
Because it's going to approach negative infinity, right? So it's okay. Think of, it's still got to center at 0.
also just an
What would
approximation.
what would happen if those top two were greater than one?
Then it would not converge to that sum. Okay, if you remember when we did the whole the geometric series, it only has a sum of a over 1 minus r if what's true. This is only true if the absolute value of r is less than 1. Otherwise, we can just completely ignore that. It's not that you don't have a geometric series, it just won't. It'll diverge and it won't converge to this function.
I understand. Like,
The series.
Okay, this is just a team. Keep in mind, we like spend a lot of time on this chapter. So this is just the very first part of it.
Can you have functions that their series diverge and not converge?
Can we have what?
Series that their function diverge and not converge.
Well, it depends what kind of series.
For a function.
That
Then you take the Taylor series and it does not converge.
But the point is, for all, like, we want to make them converge. Okay? So when we do convergence or divergence, right? So if it was just in terms of like n, right? If it was just a series with n, it didn't have x, like a variable, then it's either going to converge or diverge. But if it has x, what we're trying to do is we're trying to find values for which it will converge to that function.
oh.
It'll make more sense when we
Oh,
get
I
into
get
10.4. Okay, like baby steps. Okay. All right, we're going to use the table of the Maclaurin series above to make this much easier. So what we want to do is we want to construct the first 3 non-zero terms and the general term. And then we want to give the interval of convergence. Okay. All right. So if you look above, do you see the pattern for cosine? It's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, so on. So if I replace all the x's with 2x, so it's going to look like this. The first term is not going to be any different. So the first term is going to be 1 minus 2x squared. Yeah, it's fine. You can just leave it like this. Sometimes I said this pattern is easier to do. 2x to the 4th over 4 factorial. Okay, negative 1. Now we want to come up with, so first 3 non-zero terms. Now we want to do the general term. So negative 1 to the n, and then we have 2x to the 2n over 2n factorial. And it continues. Are we okay with that? that. So in a case like this, I would not try to like simplify anything. Just leave it. We can see the pattern. Okay, so now this is going to be true for all x.
It's really cool that it does that.
When would it not be all x?
Well, cosine and again, e to the x, cosine x, and sine x are for all real x. They're going to converge.
Because the derivative is like
Yeah. Think about like cosine and like think about those.
Why does e to the x converge? I mean, why does it work for all real x's if it doesn't converge?
What do you mean if it doesn't converge? Oh, you mean the actual function doesn't converge? Okay, just because a function doesn't converge doesn't mean we can't come up with a Taylor polynomial that converges to that function.
For all real x.
Yes, that's what we're doing.
That's pretty cool.
It is actually very cool if you think about it. If you don't think about it, fine, just memorize it. If you want to do well, then just memorize it, whatever. Okay, e to the 4x is going to be what?
1 plus 4x plus 16x squared over.
Perfect. 1 plus 4x plus 4x squared over 2 factorial. Pattern is 4x to the n over n factorial, true for all real x.
Do we write for all real x? Like that?
Yeah, because you need an interval. Oh, you can also do like negative infinity to infinity. Doesn't matter. Okay, next one is a little tricky.
I can do that.
Is the same as 1 over 1 minus x except it's x.
Okay, so if you think back to what was 1 over 1 minus x, that was our geometric series where it was 1 plus x squared plus, right? And so on. Okay. Well, what if I replace the x with an x squared?
1 plus x squared.
Okay, so 1 plus x squared plus x to the 4th plus x to the 6.
8,
Okay.
10.
So this is going to be x times 1 over 1 minus x squared. Think of it that way.
So then it's just x and then x cubed and then x cubed.
So x times x then.
So
it's all the
x-
odds instead of all the evens.
So it's going to be x plus x cubed plus x to the 5th plus x to the 7th, dot, dot, dot. Okay, what is our pattern?
X times x then. Does that work? Then x then plus-
Okay, if even numbers are expressed as 2n, this would be
It is x times x cubed. Is it
odd numbers are 2x plus 1. Think about that. When n equals 0, I get x to the 1st. When n equals 1, I get to the 3rd.
It's the 2x plus 1.
And this is going to be true for... Oh. Are we still learning?
Yeah.
Oh, we're on the last example. Okay.
Okay.
This is true for what values?
When the
-1 to 1.
I love.
Hooray.
I just want to say I don't really love that notation.
Wait, why is it?